So welcome you all to the inaugural GIAN course on 3D digitization for cultural heritage. So we are very happy to welcome you all from all over the country to IIT Gandhinagar. So the course instructor is with me, Dr. Marco Callieri. He is a researcher in ISTI-CNR Pisa, Italy. And I am Shanmuga, who would be the course coordinator. I won't be teaching any course, but I would be like kind of doing the logistical arrangements for the course. So Dr. Callieri is very famous as a developer of MeshLab, which is used all over the world, as well as recently he has developed a new tool called 3D Hub, which is a 3D heritage online presenter. So I am very excited about the course as much as you, and I welcome all the remote viewers across the world who are seeing this course through live streaming, and hope you enjoy the course. I hand it over to Dr. Marco Callieri. Thank you.
Thank you very much for the introduction. So I'll also start with an introduction. So repeating some of the things that I said yesterday, my name is Marco Callieri, I come from Italy. I studied computer science. So even though a lot of my work is in cultural heritage, I'm still a tech guy. So I work on 3D computer graphics, most of all 3D data manipulation and rendering, especially when a lot of data is involved. This means that 3D scanning and 3D digitization was a good territory for people like me to experiment, find new algorithms, find new methods. This is my email. If you have questions or things that you need to ask, I will possibly respond in a short amount of time, even when I'm here. So, but in any time you can stop me and we can discuss about the things I'm presenting. Okay, it's also in the end of the slides. So I work in a small lab. We are around 20 people that works on computer graphics. The lab is part of an institute that is around 200, 250 people, all work in different aspects of computer science. So network, high processing, high performance computing, digital library, this kind of stuff. This institute is part of a nationwide institution, which is the National Research Council of Italy, that is an institution of research, and it works on any topic, so humanistic, chemistry, physics, geographic surveying, everything that is research is managed by the National Research Council. So our group works in 3D computer graphics. Some of the people, and not the majority of the lab, but a large portion of the lab works in cultural heritage. So applying 3D computer graphics on the problem and on the topics of the preservation, documentation, restoration, and presenting to the public of cultural heritage. So we have worked a lot in 3D scanning, so creating 3D model of object, using those 3D models to measure something, so to help the understanding of the object, or to study the evolution of a situation like archaeology. We worked a lot on color mapping, that is a huge problem in the digitization of real-world objects, and presenting the 3D artworks to the public. Other people in my lab work on real-time rendering, so things about simulation for medicine, and yeah, this is also medicine, about how you tie the wounds when you have in surgery simulation, real-time rendering of huge data set like planet sites survey, or urban environment, so efficient rendering of complex three-dimensional data set, which are quite different from the thing about cultural heritage, but still you have a completely different way of representing things like these, or biology, or texture mapping, and a lot of other stuff in the real-time world. And there's a core of the group that works on the basic algorithm. All the basic algorithms are the manipulation of three-dimensional data structures and a lot of geometrical, algebraic, mathematical operation that you can do when you have a three-dimensional data structure. This is cross-field, so it works across all the different application field. So the people in our lab that works in this geometry processing thing prepare a lot of the algorithm, a lot of the software, a lot of the more technical solution that we use in the different field, may it be medicine, may it be cultural heritage, may it be the other things that we work on. So, our everyday work, our main funding comes from European project and national, regional project, and a few industry contracts. So we get paid to develop a specific piece of software or to go and scan specific artwork or a specific situation. We have active collaboration with a lot of universities in different countries, both Europe and US, also something in Asia, but not so much. And we teach courses. We teach courses because we like teaching, and we think that as a researcher, the teaching is part of your assignment, even if it's not mandatory. Communicate what you have learned and try to have people understand the thing that you have researched is part of our mission. So we have courses in the computer science department, but also in the digital humanities department. So trying to have people that have a different background understand also the technological part that's involved in the study of cultural heritage. We have PhD courses for the University of Pisa and another institution nearby that has PhD doctorates. And then we organize courses in the framework of other European projects and other activity for postdoc, professional, and other figures. So, as I said, we work a lot in practical, applicative projects. So, even though we are researchers in computer science and we develop algorithm and methodology, it is often the case that we apply those algorithm and methodology in practical program, not only in the field of cultural heritage, but also in other fields. However, since we are computer scientists and what we do is write programs, we are keeping up open for the people that need to use it, a series of tools. We have a lot of custom one-shot tool to solve a very specific problem, which are those kind of prototype that you normally find in research, that you are able to work with it if you created it, and if it's still 1 week after you created it, and after a while you just forget how it works. But we are trying to maintain some tool usable for the community, so we are trying to document it, to keep it updated, and to work on it. The three main tools that we give to the community are the VCG library. It's an open source C++ library for 3D data structure management. So you find inside a series of basic algorithm and basic data structure to represent three-dimensional data inside software, C++ software. So meshes, triangles, point, quad meshes, vector field, this kind of stuff, and all the algorithm about simplification, topology, geometrical computation. And so this is more for the developers. And we have two tools that we are giving to the community, and well, this one is really used a lot, especially in the cultural heritage community. One is MeshLab. It's an open source tool for 3D mesh processing, editing, and visualization. So you will see it in the course, because most of the things that I'll show inside MeshLab, because it's usable for most of the things that you may have to work in this course and in your work on cultural heritage. It's open, it's free, so it's a good way to start trying things before you actually maybe commit to more expensive software, more expensive hardware. So you're able to try and see things and work it with your hands. The other is 3D Hop, is quite recent. It's a tool for the visualization of high-resolution 3D model on the web. This is another tool that I will present during the course, because when we speak about the presentation, when we will speak about the presentation of 3D model over the web, I will show some of the existing tools that are available, and then I will explain how to use this as a way to present your 3D data on the web. Again, it's free, it's open source, so it's a good way to start doing some work and to explore this kind of world. So MeshLab. MeshLab started as a project for a university course in 2005. So it turned 10 this year, and it started as an experiment. So instead of giving, in the computer science course, instead of giving the usual assignment, create a program that loads a mesh and display it on screen, one of my colleagues, Paolo Cignoni, wrote the skeleton of this tool and asked all the students to contribute to this tool with various algorithms to show the mesh, to simplify the mesh, to edit the mesh, to use a different kind of rendering. So it started as a project, and then it kept growing because we started putting inside it a lot of the algorithms that we work with, a lot of the features that we normally use every day at work. So it's open source, all code is distributed with GPL license. The main repository is on SourceForge. For the moment, we are planning to move to GitHub, because SourceForge at the moment is going through a tough period. It's multi-platform. Its installers are available for Windows and macOS, and the code can be compiled on Linux. Some time ago, someone did an official Debian distribution package. It's not updated anymore, unfortunately. We do not have so many people working on the project to keep it up all the possible target. However, it works well on Linux also. You just need to recompile it. It's plugin based, so every functionality is independent from the other. This means that it's easier for us to develop new functionality and to add to the software, and this gives you a very strange approach to the processing. If you have used some other tool for mesh processing, you sometimes find a very small set of operations that you can do on your 3D data. MeshLab gives you hundreds of possible operations, each one very small, so you can build your own working pipeline in order to get a good result. This does not mean that it's an easy software. On the contrary, it's a very complex software to use, but gives you more freedom of choice between different versions of the same algorithm or different parameters. So you build your own workflow. So MeshLab was a success. Hundreds of universities and research centers are using MeshLab, and it's used a lot, as I said, in the cultural heritage field, also because it's free, and many independent 3D scanners, printers, and other software, people producing other hardware and software for the 3D recommends the use of MeshLab, just even as a way to convert from one format to another, or to visualize your tool. Early this year, we reached the 1,400,000 download, which for a software that is so specialized is a very large number. And we are going towards the 2 million mark. We have a rising trend with thousands of power users. We have a way to anonymously collect some usage data. Nothing that you work on is transmitted to us. It's just that after a certain amount of mesh that you have opened or saved, one message is sent, so we know more or less that it's not only downloaded, but it's also used as a software. So the other software that we will use in the course is 3D Hop. 3D Hop is a tool for the presentation of high-resolution mesh on the web. On the web using WebGL and HTML5. The good thing is that it works without any plugin. So you just have to write your web page using this software that is a JavaScript library. You create your web page as you want, because the good thing is that the only thing that is managed by 3DOP is the rendering window. Everything else is HTML. So you're using the same stuff that you normally work with when you're creating a web page, a website, an online service, anything. And you can integrate 3D data inside it. And you can, using buttons and other HTML components, control what happens inside the 3D view. It's again free and open source, so you can download everything, the code, and you modify it for your need. And in this case, more than for MeshLab, we are trying hard to keep everything documented and properly described. We have tutorials, we have examples, so it's also easy to learn it at the beginning. It's still young. We released it 1 year and something ago, 1 year and a few months, not much. So it's really young. We cannot have the same number as in MeshLab. And we had just moved to GitHub the source code and released the new version. It's still an ongoing project. Well, this means that we are adding new feature to the to 3DOP, because we believe it's a good way. Even for us, all these tools started as an internal tool. So they are the tool that we use to do everyday job, work in a project, do third-party development, this kind of stuff. So all the things that you see here were part of actual project that in the end, instead of just providing the 3D model, we also created a way to present this object on the web, or, for example, to create interactive kiosk. There are different ways to use 3D for cultural heritage. One is more technical, so the use of the three-dimensional data as pure information. You can do calculation over 3D data. You can track changes over time. You can measure volume, space, distances, areas, and this is a technical thing. You can confront and you can measure the difference between two similar objects. You can do a lot of things that are purely technical. However, 3D has also a visual side, and especially for cultural heritage, the dissemination, so the presentation to the public of what you have found, of the object, of the meta information that you have discovered over it, it's a major field. So don't think about 3D only as a source of measurements, but also a way to communicate about the artwork and have a very large reach, especially if you use web-based communication. So, the course itself. In the course itself, I will touch some of the more used technologies in the cultural heritage field, and this will be from a technical but also practical point of view. So I will describe the technology, what's behind the technology, which are the algorithms normally used, which are maybe the open issue about the different topic. And from a practical point of view, I will describe how these have been used inside projects, how these are normally used in the cultural heritage field. I will speak about 3D scanning. We will start from here, so the devices that are able to capture reality and measure the geometry of objects. And I will speak about 3D from images. 3D from images is a rising trend. So up to 5 years ago, let's say, the only way to capture a geometry in a faithful and usable way was 3D scanning. The recent advancement of 3D from images technology, so starting just from a bunch of photos, of uncalibrated photos, you're able to create a pretty reasonable, precise, and very usable geometry, which is a huge plus because you do not need a specialized hardware to do so. And 3D from images is a rising trend, especially in cultural heritage, because a lot of the things in cultural heritage are good for the kind of algorithm that are used in 3D from images and the kind of market, in the sense that most of the tools that you use are free or very, very cheap, and you only need a camera. Always bear in mind that cultural heritage is not a very rich field. So every solution that you can provide that use existing software, that use free software, that use easy to acquire devices, it's okay. Then I will speak about data processing, so how to work with your 3D data, 3D model, and how to process all the data coming from 3D scanner, 3D from images, in order to create usable 3D models. And this is a very wide topic, so I will try to cover some of the most common problems and some of the most common things that are done to this kind of data. Then I will speak about something that is not strictly 3D, but is used a lot in the field, which is relightable image. Those images that you can change the light direction and see what's happening to the object. It's not a 3D representation of the object, but still it's extremely useful for the study and for the communication of a lot of things, of small artworks, coins, carvings, small detail. Then we speak about color and 3D. Color is a mess. Geometry is relatively easy. We have scanners, we have a lot of software, we have a lot of already existing solution to cope with geometry. Color is something that is, color and material is something that is much more complex to manage, especially when you are working in a field where the appearance of the object is really part of the object, is really part of the experience of the object. The color has been a very promising field of research for cultural heritage for a while. There are some solutions. I won't say that there are not many really good solutions to manage color, especially for the cultural heritage. Color and material. I must say that the community has let this problem a bit slip out, because there are a lot of very custom, very specific solutions, but nothing that is really generic as the way that geometry is processed. And then I will speak about publishing 3D online. So all the things that you have created and processed and measured and done, you can, and you probably will, present them somewhere. And one of the most usable options is to use the online, the web, because it's a way, and it's a very easy way to reach a lot of people, and with a small effort you can have very good result. So these are the things that I will present about the technical side, but I will keep trying to tell you everything that we have learned in these years of work in the cultural heritage field. So every time I present a technology, I will probably tell you a story about how this technology was used in some project, what went well, what went wrong, this kind of stuff, some real-world experience about using this technology in the cultural heritage world. Because a lot of this information are very wide and I won't say generic, but it's still, in order to cover in these few days all this stuff, it will be an overview, a very detailed overview. So I will try to give a complete overview of the various topics, but still I won't be able to go extremely in detail on each of these topics. So the technical side, it's easy because you have some initial idea, you will see the overview, you will know what to search for even on the resources on the web. However, on the other side, to really understand the project, what's happened in specific case, that is even more important than having a very technical knowledge. So one last thing, as I said, as a group, we do a lot of teaching. We do courses for the university, for PhD, and for professionals. So some of the material that you will see in this course It's not all made by me, but also by other people in the lab, mostly by my colleague Matteo Delle Piane and the head of our lab, Roberto Scopigno. These are the two main contributors for the slide that you will see beside me. We are the three guys that normally goes around and present this kind of topic. The other people that contributed in the work, I will try to cite them as we go on and we reach the different things. I just wanted to acknowledge these other contributors to the course. So, let's start with the 3D scanning. Please interrupt me if I say something that you do not understand, or if you have a question. I will stop regularly and ask if there are any questions. However, if I do not stop, just stop me. This is again my email, and we can go to the first topic of the course. So, most of the things that I will show will involve a digital model of real-world object. A digital model is a geometrical and mathematical representation inside a computer of a three-dimensional object. Three-dimensional object, so we represent generally an object using a series of points and triangles. So everything that you will see that looks like an object, it's in reality just composed inside the computer by a series of vertices and triangle. Most of the models that I will show come from 3D scanning. What is 3D scanning? 3D scanning is not just a single technology, it's a family of technology, and quite a large one. It's important to understand one thing. 3D scanning in all its variation, in all its devices, in all its methods and way to use it, it's a form of automatic measurement of geometric properties of objects. So everything that's come from 3D scanning has a metric quality. This means that the object does not look like its real-world counterpart. The thing that you have in your computer has the measurements taken from reality. So you know exactly how large is it, all the possible measure, and moreover, you also know that the object, the data that you have has some kind of error, because error is a part of being a measurement. Scientifically, if you have a measurement, you have an error. So it's important, beside of knowing that that model has been generated using 3D scanning, so measuring reality, you know exactly how it was created and how much error does the object contain. In this way, you will have scientific data. That's important. If you want to show some nice stuff to someone, this thing is not really useful. But if you are using it for scientific purposes, to help the restorers to document the object, to do a scientific presentation to someone, this thing is extremely important. So 3D scanning is measurement, is automatic measurement. Automatic because everyone is able to get a ruler or a compass and measure manually an object. The thing about 3D scanning is that it tries to do as much as possible of your measurement in an automatic way. So it's automatic measurement of geometric properties. Geometric properties because everything that you will see is just geometry. So 90% of the 3D scanner only capture geometry. Very few capture color, and that's a pity. So, actually, measurement is just one step. One may have the idea that 3D scanning works as 2D scanning, where you just put an image, a photo, a piece of paper on top of your flatbed scanner, push a button, and you already have a faithful digital representation of your 2D image. This is actually not the case. Unfortunately, 3D is a bit more complex, even just because it has the third dimension, so you cannot work on an object only from one point of view, but you have to move around the object. So the object, you have to follow the entire shape and the entire sides of the object. So even in this case, it's even just for this reason is a situation that is more complex. So things are slowly changing. So especially for a certain class of scanner, especially handheld scanner or scanner that have been designed in order to be really, really easy to use, you have something that looks like the 2D scanning. So you push a button, you move your scanner, and at the end you get something that is more or less a complete 3D model. But it is not normally the truth, especially when you have to, when you need to have very complete data, very precise data, using high-end scanning devices. There's a lot of work involved. So measurement is just a very small step in what is normally called the 3D scanning pipeline. This goes under a lot of names, the processing pipeline. But the 3D scanning pipeline is the process by which you go from nothing to have your 3D model ready and usable. So at the beginning, there's a phase that it's somehow in the board, it's the acquisition planning. So before actually starting to digitize an object, you have to have an idea of your strategy, of which part will be easy to acquire and which part will not be easy to acquire. You have to forecast the possible problem in the digitization. So this part is part of the pipeline, but it's something more philosophical, more about the organization of the work. So the acquisition is just here, and this is the only part when measurement happens. So all the data is created here and just here. Everything else is manipulation of the data, so something that transforms the previous step in something else. So here you acquire geometry and you introduce some kind of error because you are measuring something. So measurement equals some error. Then you can process your data, and every time you do some of this step, you introduce some more error. So every time you are changing a bit the data in order to go to the next step. The important thing is to keep track of this process and to know exactly what happens to the data. Before, in the end, you want to arrive here to the archival and use. When you have something ready to use, you do not just need your 3D model. You also need what is normally called metadata. So everything that documents what happened to the measurement and what happened to the data. This is extremely important in every field of science. So knowing exactly what happens to your scientific data, and it is extremely important also for the cultural heritage community, because 1 year from now, 10 years from now, 20 years from now, people will maybe look at this 3D model, and if they find some documentation on how the model has been created, the model will be useful 10. If you just find a 3D model without any description, you know nothing about how the model has been created, how it's been processed, which was the error expected, which was the device used, this is just a toy. It may still useful, it may be still useful like 2, 3 in a level of 1 to 10, but you are missing something. And especially in the cultural heritage, data may be retrieved and used 10 years after has been collected. So it's extremely important to keep track of all that happened to your data as precisely as possible and as detailed as possible. So you want to write down things and keep that metadata inside your 3D model. Well, not inside, beside your 3D model. When you archive your model, you archive also the process that came with it. So, measurement. I say that 3D scanning is a family of technology, so let's have a taxonomy of the scanning. There are many different ways to organize a taxonomy of 3D scanning. This is just one that is easy to use for the presentation. So we will split in two. We will split in technologies that have a contact with the object and technologies that stay at distance. And we will start on these sides because it's the least diffused, so it's easy to manage. Up to some years ago, people used slicing to produce 3D representation of objects. So they had an object, especially in the case of biological sample and similar things. They congealed the thing or they immersed it in resin and then thinly sliced the object and then scanned each slice. This was a way to create a three-dimensional model, actually a three-dimensional volume of the data. It's still used in medicine, but not really much in cultural heritage. One thing that is still used a bit is the use of articulated arm. Articulated arm are things that are similar to this one. So you have an arm with an encoder, an angle encoder in each of these joints. So since this is a rigid object and you know the angle at every joint, you know exactly where the touching probe is. This kind of stuff was made for people in the entertainment industry because they could manually go and model 3D model just on top of an existing object, but also for industry. In industry, you sometimes need, instead of having a complete 3D model of an object, imagine having a car or a similar thing, you may just need a profile. And if you scan an object, you get thousands of points, millions of points, but nothing guarantees you that you really get that profile that you really need. So these things are still used in industry, using a physical arm or sometimes another kind of tracking, but you still probe the object. And there are industrial sensors that are precise in the order of microns that are touch sensors. So you have an object, normally a mechanical piece, you put inside a box, and there's an automatic robot that touch the object at a regular interval. These are the most precise measurement devices that exist, because on a very large object they can go to microns, but again they are not very used in the cultural heritage field. Because in most cases you don't want to touch the object. A lot of cultural heritage artifacts are fragile and people really don't want you to touch it. So everything that stays away from the object is good. So we will concentrate on the distance, so technology that is able to read the object from a distance. We will split again using non-optical methods and optical methods. Non-optical means to use everything that has been created using non-visible energy. For example, this is a way, not really 3D scanning, it's not really considered in the family of 3D scanning sometimes, but still using PAT, CAT, or magnetic resonance, you obtain geometrical information about your object. You actually obtain much more. It's not just geometry. You obtain a lot of information because you get a density value for each point of your object, each point in the volume of your object. So this, instead of being just an information of the geometric shape of the object, so of the external shell, you are going inside. You also get information of all the objects that are contained in your artwork. These technologies are born in medicine, but are also used in industry. Sometimes they use not magnetic resonance, but X-ray and computerized tomography, also on mechanical pieces, in order to see stress, internal stress of the metal, or to assess how good a cast has come out. So they are used a lot in these two fields, but have been used in cultural heritage. This is a constant. Cultural heritage field borrow devices and software from other fields. So thing that you may have seen in technical journals, also in sometimes even in newspaper, is the use of CT scan, for example, on mummies, because most of the mummies are very closed objects, so you want to understand what's inside, and some have been torn open in the 18th and the 19th century. Now they try to keep them as intact as possible, so most of the work, most of the diagnosis work, or most of the consolidation work, most of the periodical assessment of the state of the artwork is done using non-invasive technologies like CT scan. So mummies are the one where this technology has been used a lot, because at the beginning they only had CT scan for human bodies. So since a mummy is a human body most of the time, they also have cat mummies and other animal mummified, especially in Egypt. It was good, it was pretty easy to think about, let's use this CT scan normally used on patients to study a mummy. And now there are available CT scans that are very, very detailed, and they work on a much smaller object. So they are normally called micro CT scan. They are used, for example, well, in this case was a collection of coin. It happened frequently in the history that people had to left home quite fast, so they buried the coin in a sack or inside an urn somewhere, and things got forgotten there. And when archaeologists find these treasures, they are called treasures, it's all a solid block of metal and ground and everything else that accumulated in the years. So they cannot take the coins apart. So one solution is to CT scan the object, and then they have a 3D model of all the of each of the coin. Or a recent trend is to use CT scan for books, manuscripts, and paper in general. Again, old books, old manuscripts, old rolls of paper or parchment. Parchment is paper made from skin of animal, generally. And they are fragile, and it's almost impossible to unroll them. Or maybe in another case, I saw a very nice work about scanning a half-burned book. So the book was in a fire, half of it burned. It cannot be opened anymore, so they sealed using some resin, and so they preserved the book, but they cannot read anymore. But in micro CT scan, you can actually get to the point of seeing the individual pages and the ink on the pages, especially because a lot of the ink in the past was made using iron. So it's metal there's metal in the composition. This means that in a CT scan you get a very diverse density between the page and the ink. So people were able to read inside a rolled paper, a rolled parchment, or inside an almost destroyed book by using this technology. All of these methods produce a volumetric data. Volumetric data is three-dimensional data, but it's much more complex to manage because it's huge. Because when you look now at an object, the volume the object occupies and the surface of the object there's a relationship. If you think about the volume of the object, the volume is much more. So in this case, you get one density value for each point inside a volume of the object at a certain resolution. So there is much more data, and the data is completely different from what you will normally call a 3D model of an object. So the software that you will use to work on volumetric data is completely different from the software that you will use to work on 3D model. So these are also devices that are much harder to acquire and much more expensive to use. A CT scan costs a lot of money to buy it, but also to use it. So with respect to scanners and 3D from photos and other methods by which you can acquire a geometry of your object, CT scan is really much harder to use. So I will present it only here, and I will not touch it probably anymore in the course. Know that if you are able to go to an hospital and have access to a CT scan, nowadays all CT scanner machines have a standard output. It's called DICOM format. If you maybe some of you had to go to an hospital because you broke one bone, they did a X-ray on you, and they gave you a CD maybe, and that CD, it's a standard format for all the data coming from X-ray machine, 2D and multi-slice, tomography, magnetic resonance. The good news is, since there's a format, a standard format for this kind of machine, there also exists some tool, even free tool. There's a very good tool for Mac OS called Osirix that is able to read this volumetric data. What you normally do with volumetric data is to extract shell, to extract something that has more or less the same density. So a CT scan gives you this. This gray color is not the fact that your brain is gray. Yes, also your brain is more or less gray inside. But in this case, this color here means that the density in this point is different from the density on this point. So since you have a different density, you can ask the software to extract the threshold between one density level and the other density level. So from this scan, you can extract the shape of the skull, because you ask the software to get everything that has the density of bone. You can extract the brain or even parts of the brain by segmenting this three-dimensional image using density. What you get out of it is a 3D model in the sense that we will speak about. So it's a model, it's a representation of a surface made by points and triangle that is a representation of a real-world object. So one way to use volumetric data is to go from here to something that is a 3D model of points and of vertices and triangle. Another way is to directly work on the density as a volume, but that's a thing that personally never did. It happened that they brought us a CD with the scan of a head of a prehistoric man, so we did this process. So we extracted the isosurface of the skull, we combined multiple scans in order to get the entire skull, and we gave the 3D model for visualization. So this is the world of non-optical scanning. Let's go to the other side. Let's go optical. Why going optical? Because it's the visible spectrum, or the near visible spectrum, because I will call optical also things that are not strictly visible. We will see probably one of the scanner or today or tomorrow, a time-of-flight scanner. That scanner has a laser that is not visible to the naked eye, but it's still near visible, so it's very near to the visible range of human eyes. And since it's close to the visible range, you can use all the existing hardware that has been created for redirecting light, measuring light, and so on, and creating light. So you will use lamps, you will use laser diode, you will use standard optical lens, standard optical filter, CCD, CMOS sensor. So all this hardware, since it's used a lot by industry, entertainment, consumer product, it's extremely cheap, and it's available in many different variations. That's why going optical is a good idea, because you can reuse all the stuff that you are using normally for creating a projector, a digital camera, and moreover, if you remain on the visible spectrum, the amount of energy that you throw onto the object is extremely limited. So one question that we always get from museum curators or restorers is this scanning damaging my object because you are using a laser on the object? And you may know that laser is sometimes used to clean an object. So you clean a stone surface or a metal surface by using a laser. So they ask, all this energy that I'm pouring onto the object can damage the object? The answer in most of the cases is no, because the amount of energy that you use for 3D scanning, may it be a laser or may it be a standard light source, is really in line by the amount of energy you will get just illuminating the object with a normal lamp. So the laser in our old laser scanner is a 5 milliwatt laser. It has the same power as this one. You know that laser is used also to remove tattoos, and in that case it's 2 orders of magnitude the energy of this one, and the same happens for the cleaning of stone. So you're going optical, you're going with frequencies that the object is already subject to. Sunlight, artificial illumination, maybe a laser pointer here and there. If the object is sensible to light, it will be stored in a box in a dark room, and that's another story. You will probably need to use something else. But optical is also so used because of this reason. Because with optical things, since you're already illuminating the object for other purposes, optical is normally safe for the scanner, for your object. Then there are 2 things that you can do using the optical, 2 ways of capturing the 3D geometry of an object using optical principle. One is going passive. Passive means I'm not introducing any illumination in the scene. I'm just looking at the scene. Your brain can understand the 3-dimensionality of a scene just because you happen to have 2 perspective cameras in your head. 2 perspective cameras that are slightly offsetted one to another. So your eyes are perspective cameras, so the image inside each of the eyes is generated using a perspective projection, and you have 2 eyes. If you, like me, have a very dominant eye, this thing is not so true. But the 2 image arrives at the brain separately. Actually, this is not even true. You your brain does not receive two images, receive a series of stimuli that are much more complex than a single image, because you receive vertical lines, horizontal lines, diagonal lines, then patch of light, then patch of color, then gradients. So your brain receives much more than a single, than two images. These two images are combined by the brain in one single panoramic stabilized image, because if you move your head like this, even if you're not a chicken, you will try it with holding a chicken that the head is completely still. Your brain stabilizes your image. That's why you think that with the camera you stay perfectly still, but it's always blurry. But your brain is able to stabilize this. So it fuses right eye and left eye in one single image, and while it's doing so, it recognizes the same detail in both of the image, and depending on the apparent movement, on the parallax of the two eyes, is able to determine the depth of the scene. So if I come here, I can clearly detect that this is closer than this other monitor. And this is a thing that the brain does automatically, and so a computer can do the same. So by providing multiple perspective view over the same scene, you can reconstruct the shape. If you go one step further, so you do not have just two images, but you have multiple images, so you have a multi-view stereo, you can actually reconstruct shape which are much more complex than this idea of this monitor is closer than the other monitor. By the way, in the human brain, this works for the first 3 or 4 meters. Then everything else is flat, because the parallax, the distance between these two eyes, is more or less 10 centimeters, so it's not that much. In this case, by taking multiple photos from different points of view, you are creating a parallax which is much wider, much larger, and exploiting the fact that the computer has time and processing capability in order to go and look at every pixel of all the image that you propose him, is able to create a convincing 3D model. So all these goes under the name, that many different names. 3D from photos is one of the most used, but you will find this family of technology again under multi-view stereo, dense stereo match, dense photogrammetry, or a combination of this term. This is another thing. 3D scanning and all this kind of technology have born in different fields, and each company uses a different terminology. So sometimes you see the same kind of stuff named in different way. I will try to show you the details so you can recognize, even if someone call it with another name. But so all the software that create 3D from image use the same basic technique. So it rely on the perspective projection and rely on the fact that you have more than one point of view. And the processing that is done to create the geometry is more or less the same for all the different software and all the different tools that I will describe. We will spend at least one day on 3D from images, because it's becoming really, really important. It works really well. I mean, I'm a 3D scanner guy. I started working with 3D scanners, and 3D scanners have a lot of features that made them still useful and valuable. 3D from images, especially for cultural heritage, or even for other topic when you need quickly 3D model, it's a good choice. So we will spend some time on this. So 3D from images, it was the way back then in which from airplane and satellite you got three-dimensional map of the terrain. So up to the, let's say, up to the 80s, also in the 90s, most of the altitude value, so the map, the geographical data, came by using 3D from images. So you had planes and satellite with calibrated cameras. I will tell you with a calibrated camera is in the appropriate lesson, facing downwards or facing down with a slight angle, going over a terrain. So the parallax was the motion of the plane or the motion of the satellite. Now, on both planes and satellite, you can have active scanner, and it's normally the case now. And if you go very small, and now there's this trend of drones, so unmanned aerial vehicle, all of these are now using this modern version of 3D from images. So they are not only relying on the fact that they are moving straight on a straight line, very precisely, very slowly, but they just hover the area and take multiple photos, and from those photos you get a pretty good 3D information. You can also do it with a kite. And I know a guy that is an archaeologist and uses a kite very much because he works in the north of Africa when there's always wind, and when there's too much wind, the drones are not so good, and drones need battery and a lot of, while kite, everyone can fly a kite. And I've seen some reconstruction and I'm pretty amazing with just homemade kite with the one with that you can steer with the two wire. So let's finish with the most used one. So the instance optical active technology. Active means that instead of just looking at the scene, I'm introducing some illumination in the scene in order to understand the geometry. So how do you measure something using just optical components and some light source? Using very simple principle. That's that's a nice thing. One of the principles that are used is triangulation. So light is projected on the surface, so you have some light emitter. It may be a laser. Why a laser? In most cases because laser diodes are cheap. They last forever. So with respect to a normal lamp, a laser diode lasts forever. And you can turn on and off like this, and the illumination is immediately at the perfect level. This is why people think that laser is used in triangulation because it has a certain wavelength. This is not true. Any light can be used in triangulation. Laser is used a lot just because it's the most convenient light that you can use for this thing. So you have your object, you see this wonderful work of art, you have a laser, you illuminate one point, and here you have a camera. You know at which angle you projected the laser, you know at which angle you saw the illuminated point, you know which is the distance between the emitter and the receiver because we have constructed the scanner, so you can determine this point in space. How far is the illuminated point from the scanner? Triangulation was used by Egyptians to calculate the measurement for raising the pyramids. So it's not exactly a new method of measurement. The thing about 3D scanner is that this measurement is done hundreds of thousands of times per second in an extremely precise way. In this sense, again, it's an automatic measuring process. As I said before, 3D scanning is automatic measurement. All the point is I have to do it quickly and in a very precise way. That's it. And the only thing that you need to construct this system, beside the electronic hardware, are optical components. So a camera, normally, and a laser projector. let's get to some hardware. So I will start from this one for historical reason, because it's the one that we started with as a 3D scanner. It's no longer in commerce. It was a commercial scanner by Minolta, Konica Minolta, and as most of the things that you will see has been created for the industry, for quality control, for reverse engineering. Reverse engineering is a good way to say I'm stealing the idea from my competitor. So you get a piece that someone else designed and you digitize it and you get the data out of it. It was used also in medicine sometime. It's a triangulation laser scanner. This is the camera and this is the laser. It projects an horizontal laser line that sweeps the object. And the triangulation is done in this way. So you can reach an accuracy of around 1/3 of a millimeter. When we bought it, it costed like 30 to 40,000 euros. Now it's you can find it used. It was used a lot in cultural heritage because for how it was designed. It was a mule. It was a pack mule. So it was a very versatile thing, and it could be used in many different situations. It had not, it was not specific for anything, so it was possible to use it in any kind of situation. It was reasonably portable. It was 12 kilo, so small enough. It can stand on a tripod. And it had very good thing that it was the autofocus. So it could work between 50 centimeter and 1.5 meters. And it autofocused on the object in this working range. I will speak later about the working area of the scanner. Bear in mind that if you have a camera, a digital camera, you take a photo and you get from here to infinity. Things that are too close are blurry, things that are too far are blurry again. In a 3D scanner, you need everything in focus, so you have a very short working range. But I will return on it later. So the one good thing is that you could be near or far because he autofocused, and he had different lenses in order to cover a wide or a smaller portion of the object. So the smaller was the portion covered, the higher resolution. The wider was the wider the area, the less resolution, but you can cover larger object. We used it a lot, and if you look at many paper in cultural heritage, it was used a lot because of this reason. It's versatile, the cost was acceptable, and it worked in every condition. We worked on top of scaffolding, we worked in caves, we worked everywhere. We transported it with every possible way, so it lasted 10 years. That for a device, for a mechanical and electronic device, is way a lot. Sorry?
After collecting scan, we merge all the scan. After that, we process the scan. So this accuracy is for registered data or for processed data?
Okay. Well, I will speak a bit about the terms later. This thing, in every scanner, I will present a box like this with more or less the cost and more or less the accuracy that you can reach. It's difficult to give a single number. I will say that using this device with some care, some luck also, because it depends a lot on the acquisition condition and on the object, you can get a data that is correct up to 0.3 millimeter. So we say after all the processing, you can get data that has a resolution and level of error that are around this value. It's something now it's just something to give you an idea of the level of the precision, of the accuracy that you can reach. It's not specific because every time you get a different value or a different resolution.
Because in case of scanning, there's two type of accuracies. One is registration accuracy and other is process data, accuracy of process data. Suppose I have taken 3 to 4 scan using this scanner, and after they import the data in some software and merge all the data,
Yes.
means register the data, it will have some registration accuracy like 3 mm or
Yes, of course.
yes, and after registration we process the data, suppose create a 3D model or animation or CAD drawing or anything, and after registration the accuracy of process data is also different.
Yeah, it change in all the step of processing, so the error increase every time you touch the data. I just said 0.3 as a bound. With some care you can reach that. In many cases it was impossible, so this object, for example, we were never able to go below 0.5 millimeter or 0.7, I'll be honest. And but in other cases we can reach 0.3 millimeter even after the processing, with some care. Again, it's not an easy task, but it was just to give an idea of the range. It's not 5 millimeter, it's not 1 micron, it's around this value. It may be 3 times this value, it may be this value. So it was just an idea. So some of the data that you will get come from this scanner. Oh, I almost forgot. In this key, USB key, there are some data set for the first part of the course, so the 3D scanning and process. I will have the key pass by, and so you can download, and yeah. You may get everything out of it or just some part, but this is reusable data. You can use it for experiment and whatever. They're basically all single scans of different objects taken with different technology. So you may do some experiment later. So pass the key around and download it. So another scanner, I will try to mention only those scanners that may be relevant for this specific work. As devices, there are hundreds of different devices that you can use for a 3D scanner. So I cannot mention everyone, every possible device. I'm not endorsing any. I'm not despising any of the scanner. Just I'll give you an overview of the thing that I could experience by hand or I've seen working in specific cases. So another one, which is still a triangulation laser scanner, and it's an incredibly cheap scanner because with around 2,000 euro, which is $2,500 more or less, you can get one. And in this price range has the same price range of a good digital camera. So if your institution or museum or may afford, it's a good thing to start experimenting. So it's that's why it has such a good diffusion in the cultural heritage world. This has been created not for the industry, but for Hollywood. So the company that produced this scanner is from Los Angeles, actually Santa Monica, but they had in mind the special effect and the entertainment market. However, given the fact that it's really small, it's this size, and as very low cost, is really, really usable in the cultural heritage field, because especially for a small object, or you can go around in a museum, we just put it on a tripod. It's a very nice device for the cost. So small price, good resolution, and good result coherence. Is highly portable. The problem is it has a fixed working distance. So the Minolta has said that you can put your object anywhere between 50 centimeters and 1.5 meters. The closer it is the object, of course, the higher the resolution. In this case, you have to stay at a fixed distance, which, if you are working on a table and you put the object in front of the scanner, is fine. If you're in a museum and your object is fixed on a wall or maybe on top of a column, it's a problem because you have to stay in a certain position. And it's not always possible to keep the scanner at that specific position. It's slow. The Minolta can take a single shot in 2.5 seconds, let's say 3 seconds. 3 seconds, you may use it on a scaffolding. This takes from 30 seconds to 1 minute. You won't be able to use it on a scaffolding because the scaffolding are always moving a bit. It's also impossible to scan human being, unless they are dead, probably. And needs a bit of parameter tweaking. The other good thing about Minolta, it behaves like a camera. So where you point to an object, it autofocused and set automatically some internal parameter in order to work better on that specific kind of surface. It was not always the best guess, but it was okay. In this case, you have to manually say the object is matte or shiny, and how dark or how light it is. And sometimes for no apparent reason, it simply decides that that material in front of him, he doesn't like it. So you get absolutely nothing out of it. Instead of having one laser blade, this uses 4 laser blades that sweeps the object. Another interesting thing is that it has 4 lasers and a camera here, and 4 lasers and a camera here. You see these, and these. This is the baseline distance, so the distance between the emitter and the receiver. And we are going to an important concept. The size of the object that you want to acquire is somehow related to the size of this baseline distance. The smaller is this baseline distance, the smaller is the object, the higher is the resolution. The larger is this baseline, the larger is the area that can be acquired in a single shot. So this scanner is actually 2 scanners. So it can work on an object of this size using this set of laser and camera, and can work on object of this size using the other set of laser and the other camera. The Minolta, you have to change the length, and it only narrowed the view of the camera. So you get better, more dense data, but there's a limit. So you cannot zoom infinitely and get higher and higher resolution, because the baseline determines at which angle the visibility ray and the illumination ray will touch. Triangulation works well if the 2 angles are like this. If the 2 angles touch in this way, or if the 2 angles touch in this way, the problem becomes geometrically ill-conditioned, so you have a great reduction in precision. This is why the size of your 3D scanner, of your triangulation 3D scanner, does matter. So each scanner, each triangulation scanner has an ideal size of application. You can do things as large as this wall with the Minolta, but in chunks of this size. And this becomes dangerous because when you try to align all the data, you introduce some error and things get banana-shaped because they tend to always go in a single direction. Still triangulation, but using a different idea. So laser triangulation, you project a single laser line or a multiple laser line, but in any case you are illuminating just one area at a time and triangulated only that part. So each time it's a slit scan, so you measure this line, you move on, you measure this line, you move on, you measure this line. There's another way that it's still triangulation. Instead of projecting one single laser pulse, you project some kind of pattern onto the object. The deformation of the pattern, so you see that this line here that subdivides the object or this other line are not straight line because they encounter the surface that has a shape. So you do triangulation on the threshold of these two colors. And you increase the depth of the pattern, and so on. So when you are projecting a pattern, any kind of pattern, there are scanners that project horizontal band, vertical band, diagonal band, colored band, or black and white band, sharp bands, or sinusoidal bands. So there are a lot of different patterns that can be projected. The important thing is that you are projecting a pattern over the entire object. So everything in this case boils down to a projector that may be even one of those digital projectors that we are using now to have this, and a camera. Structured light, this is the name of this branch of triangulation, is still triangulation, because what's happening is that you have a baseline, you have an emitter, and you have a receiver that has an offset. So the principle, the mathematical principle is exactly the same. The thing is, given the amount of information you are projecting, since you are projecting a lot of information more, because it's not only one point, but you have all the pattern, you can get a bit more precise. And this thing is a bit more resilient to some of the problem that laser scanner has with shiny object and dark object. Just a bit more resilient. It's not that they solve the problem, but they're a bit more resilient. That's why a lot of the high-end metrology scanner use this kind of technology. You can build a structured light scanner with just these two components. Again, the problem is to calibrate it effectively and to write all the software. So it may be a good exercise also for the student, but unless you really want to experiment with some idea, there are already a lot of information over the web. There are people that wrote software for this, so you only have to provide the components. So there are intermediate steps. So if you really want to try building a scanner, look at the web. There are already some pretty good solutions. So as I said, high-end metrology sensors are normally using this kind of technology. So structured light. There are also metrology scanners that are laser scanner. The next, the Minolta, just not the one after the Vivid, but two after the Vivid are laser for metrology. When I say metrology, I mean Metrology is an industrial process of precise measurement. So things that you need to measure in a very precise way. So you need a very specialized hardware and a lot of care when you take the measurement. All these can come from the industrial setup, but are also used in the cultural heritage. This is one, is a German company. Strangely, the name of the German that are really precise and they are into measurement and precision is true. There are at least 4 or 5 brands of metrology instrument that comes exactly from Germany. This is one, a small company, Breukmann. I met the Mr. Breukmann is a very funny guy, and Dr. Breukmann actually was, for one time was a professor at Munich University also. So this is the scanner. Here is the projector, which uses a simple light, a 100-watt light bulb. And you see that here he has 2 cameras. So not one, 2 cameras. It's still triangulation, but it does triangulation between camera 1 and projector, camera 2 and projector, and camera 1 and camera 2. So it has this triple redundancy. And if you see, this camera has a baseline, and this camera has a different baseline. So it's able, by combining these 3 angles, projector camera 1, projector camera 2, and camera 1 to camera 2, it has 3 different triangulations. So it has a triple redundancy when it determines the position of the point. It's extremely precise. This is a basic configuration. These arms may be longer or shorter depending on your needs. So when you buy one, you can customize it. Well, you can customize it also because you pay something in the order of 70 to 80,000 euros. So if I want it with flames, I want it with flames, and they will provide it with flames probably. The lenses, again, are exchangeable, so you can change the lens and have a wider or a smaller field of view. So depending on your need, you can get a very different configuration, but this is the basic one. And with this, you easily reach 1/10 of a millimeter. With other lenses, maybe going smaller, you can reach 100 of a millimeter, but it's in laboratory condition. It's really costly. It's still usable and it worked very well. In this case, we were monitoring fractures on the Michelangelo's David. This is the Michelangelo's David, this is the rest of the statue. The David, I know how many of you know the statue, is a 5-meter tall marble statue. Since the leg position is this way, in this way, all the weight of the statue goes on this leg. So the author created on the back of the leg a trunk of a tree that help supporting the weight. In this area, there are cracks. There are very old cracks. We know that there are cracks since the 18th century. From time to time, these cracks are monitored by the means of vibration sensor all around the statue, by doing some micro analysis near the cracks. And the last couple of times, we also had the precise 3D scanning of the area, so at 1/10 of a millimeter. And then after 2 years, we came and we acquired again that area to compare the situation before and after. The fractures are stable because they are compression fractures, so they are kept closed by the weight of the statue, but there have been no chipping, so the profile of the fracture is still the same. If you have some movement, what you can expect is there's more compression and some part just chip away and you see some missing area. So this was one of the things that we did using this device. Last time we went was a couple of years ago. So 4 years ago we went for the first time to get the initial data set, and then 2 years later to get the new version.